All right, Unit 5, Lesson 2. We're going to be talking about evaluating and graphing polynomial functions. So a polynomial is a monomial or a sum of monomials. Oftentimes it's written in this form where you notice, okay, we've got n minus 1 is decreasing, goes on forever, and then we end up getting to a of sub 1 and then a sub 0. Also notice that our exponents are decreasing until we get exponent of 1 and then exponent of 0, which would just cancel out. So each of these are kind of decreasing as they go along here. A sub n, okay, so this blue part right here at the beginning, that's called our leading coefficient. N is our degree, so again, we always put the highest degree first. So if you look, a constant function right here does not have a variable. So again, it's never changing. Negative 14 is negative 14. Linear has an exponent of a degree of 1. Quadratic, exponent with a degree of 2. Cubic, exponent degree of 3. And quartic, exponent degree of 4. Just a few examples. We'll find the standard form, its degree, type, and the leading coefficient. So let's see here. We have h sub x equals x to the fourth minus 1/4 x squared plus 3. I would say that in this case, it's a polynomial function. It's already written in standard form because, again, my exponents are decreasing. So that's how I know that it's written in standard form. I would say that this is a degree of 4, so fourth degree. Leading coefficient, there's no number in front of this x, so I'm going to say that means it's a 1. So if there's no number out front, I can assume that it's a 1. And again, it was already written in standard form, so we're good there. If I look at a different example, maybe this one's not written in standard form. So first thing, again, I would set this up. I might rewrite some of this, and I'm going to say, hey, if I have a square root, maybe that's 3 to the 1/2, or really I'm thinking, okay, the square root of 3, that's just a number. I don't have any x's. So while it's a number that never ends, according to this, that's going to be my a sub 0. Because again, there's no x next to it. So if I rewrite this, I'm going to have pi x squared first plus 7x followed by my constant, which is the square root of 3. Yes, it's never going to end, but because it doesn't have an exponent, we can say that. My degree is going to be 2. Because that's my highest degree right here. My leading coefficient in this case is pi. So the number out front next to my x squared is pi. I guess we can do one more here. Maybe 1 is an example of what is not polynomial function. So say we have k to the x equals x plus 2 to the x minus 0.6 x to the fifth. Because we have an exponent that is a variable, this would be an exponential function. So this is not a polynomial function. This would be an exponential function. So again, one of the ways that we can evaluate polynomial functions is with just direct substitution. So if I take the formula f of x equals 2x to the fourth minus 5x to the third minus 4x plus 8, and I want to find when x equals 3, all I'm going to do is I'm going to take this, and every time I see an x, I'm going to plug in this 3. So I'm going to rewrite this equation. Again, trying to find when x is 3. So now I'd want to simplify. I'd want to find out what's 3 to the 4th power and then multiply it by 2. I believe that gives me 81. So 81 times 2 gives me 162. 3 to the 3rd is 3 times 3 times 3 is 27. 27 times 5. And it's negative. So that's going to give me, what am I doing down here? 162. And that's going to be subtracting 135. Negative 4 times 3 is simply just negative 12. So I'm going to subtract 12 and then add 8 at the very end. So 162 minus 135 minus 12 plus 8 is going to equal 23. So we can sometimes use direct substitution. If I know what x is, I can just plug these things in to figure out what goes in there. Now, we have another way to evaluate functions through synthetic substitution. And this is a kind of like a, I don't want to say a trick, but this is like a strategy that you can use to solve unknowns. So if we take that same exact problem, so we're going to take this same problem here. Okay, but let's say we didn't want to use direct substitution. Well, what we could do is we could take, and again, we still want to find it when x equals 3. So I'm going to set these up. I'm going to take my x value and I'm going to place it right here, which is 3. And then I'm going to line up and take all my coefficients and put them over here. So again, my coefficients are the numbers out front. 2x to the 4th, negative 5x to the 3rd. Notice we skipped x squared, okay? X squared, So because we skipped x squared, I need to include a 0 here. So this is going to be 0x squareds minus 4x, and then my constant is 8. So make sure that when you're using synthetic division, okay, when you're doing this, if you skip a variable, like we skipped x squared, you have to correspond that with a 0. Otherwise, it's not going to work. All right, so what we're going to do is we're going to start by bringing down this first term right here. We're going to bring it down and have it at 2. And then we're going to multiply by our x value. So I'm going to say, okay, 2 multiplied by 3 gives me 6. And then I'm going to subtract these. I'm going to add these. So then I'm going to add, okay, negative 5 plus 6 gives me a 1. So now that this number goes, okay, 1 times 3 is 3. 0 plus 3 gives me 3. 3 times 3 gives me 9. Negative 4 plus 9 gives me positive 5. 5 times 3 gives me 15. And 15 plus 3, or 15 plus 8 gives me 23. So now what I do with these numbers is I would get a final answer, and I would say, okay, because I got an answer of 23 here, I would say that f of 3 equals 23. So I'm just going to kind of list out your steps for synthetic division. Synthetic division. It's what we just did. You want to bring down the coefficient. You want to multiply by the x value. And then you're going to add the last two numbers, the two numbers that are stacked. And you're going to add, and then you're going to repeat. You're going to move it over and then repeat. Okay, so two kind of graphing examples, questions to talk about, and then we will be done with this lesson. So this is important for you to write down and to get this example into your notes. Looking at end behavior. So again, a lot of stuff can happen inside or in between the function, but if we look at and we focus on the end behavior, there are specific things that we can learn. So for one of those is that if I have an odd number degree, so again, odd number degree meaning like 1, 3, 5, 7, 9, 25. That means my highest exponent is an odd number and I have a positive coefficient. Okay, as I move, as my x's go, my y's are also going positive. Okay, whereas if I have a leading coefficient but it's negative, as my x's are getting bigger, my y's are getting smaller. And it's vice versa. So again, notice, hey, when I have an odd degree, I have one end behavior that is increasing, and I have one end behavior that's decreasing. However, when you look at an even degree, so again, that's like being a 2, a 4, a 6, an 8. So what's that highest exponent? As my x's are getting smaller, my y's are getting bigger. And as my x's are getting bigger, my y's are getting bigger because I have a positive leading coefficient. If I have a negative leading coefficient, then as my x's get smaller, my y's get smaller. And as my x's get larger, my y's get smaller as well. So even end behavior, if you notice, they both end up going the same direction. When I have an even degree, my endpoints are either both increasing or both decreasing. Whereas when it's odd, you're going to have one that's increasing and one that's decreasing. So just looking at the end behavior, you can determine some of these things without even graphing. So we'll do one kind of graphing example here. Again, good to be able to graph by hand. You will be expected to do that. So let's see here. Graphing, question A, part A, f of x equals negative x to the third plus x squared plus 3x minus 3. So again, there's kind of lots of ways to do this. One good way to give yourself just a general rule is to create a table of values. So what is the answer going to be when x is negative 3, negative 2, negative 1, 0, 1, 2, 3? It might be a little overkill, but again, it's good for you to have more information than not. So when I plug in negative 3 into this equation up here, I'm going to get, if I plug in negative 3 into this equation every time I see an x, I'm going to get 24, 3, negative 4. Again, I would use a calculator to help you. Negative 3, 0, negative 1, negative 12. So if I'm just looking at some of those things we just talked about, my degree is odd. So again, I know that one end is going to be increasing, one end is going to be decreasing, and my leading coefficient is negative. So if it's odd and negative, I can expect my graph to look something like this. I know it's going to be something like that at the end. All right. So let's hear 1, 2, 3, 4, 1, 2, 3, 4. Just good to get at least a few of the numbers in so that I can see the scale that you're using. So when x was -3, y was 24. That's going to be all the way up here. So again, it's going to be somewhere up here. When x was -2, y was 3. I can graph that one. When x was -1, y was -4. So that's going to be down here. When x is 0, y is -3. When x is 1, y is 0. That's a 0. Super important. X is 2, y is -1. And then when x is 3, y is -12, which again would be all the way down here. So if I were graphing this, it'd be something like this. Comes down here, scoops up here, and then decreases like this. So again, we've got an arrow pointing up and to the left, arrow pointing down and to the right, which is kind of what we would expect right there.